Hello everyone, I am Minxue Pan from Nanjing University. It's a pleasure to introduce our work, Reinforcement Learning-Based Curiosity-Driven Testing of Android Applications. It is well known that Android applications are event-driven. In other words, the application business logic is fulfilled by the functional calls activated by GUI events. Therefore, most automated testing focuses on GUI testing, and we make no exceptions. One of the biggest challenges is the large combinational space of possible interfaces and executable events. A daily used app usually contains plenty of interfaces and executable events, which makes it time-consuming to explore all the application states. Many different strategies have been applied to automated testing of Android applications, and they have their own pros and cons. We roughly categorize these methods into 4 classes. Random testing generates test events with high efficiency, but it often generates futile events. Model-based testing generates test cases according to models. We know that it is almost impossible to precisely model the app behavior, which could be a problem. Systematic testing is designed to reveal hard-to-reach functionalities, but it may be less scalable and performs poorly in overall metrics. Machine learning-based testing can benefit the Android testing. Q-learning is a reinforcement learning algorithm that does not need a specified policy. It seeks to find the best action to take, which is particularly suitable given the goal of automated testing. It also avoids the inconsistency problem between models and app behavior. However, existing works do not fully unleash the ability of reinforcement learning in Android testing. For example, prior works tend to calculate the differences between 2 states to determine the reward. If the states are quite different, the testing tools will continually give a large reward, making the testing process frequently jump between the 2 states. We propose a novel approach, Q-testing, based on Q-learning. The strategy of Q-testing is called curiosity-driven exploration, which guides testing towards the unexplored states that it is curious about. This is the workflow of our Q-testing approach. We can see from the figure that it is an iterative process. In each cycle, Q-testing first observes the application's current state using UI Automator. Then, the state is compared with part of the prior observed states that are stored in a buffer acting like Q-testing's memory. The comparison is conducted by a trained neural network. If the current state is similar to any of the states in the memory, a small reward will be given. Otherwise, a large reward will be given and the current state will be added to the memory buffer. The reward is to update the Q values of the interactive events stored in a Q table. The update follows the Bellman function. Note that Q-testing can infer the executable events from the GUI hierarchy. And with the updated Q values, it will choose an event with the highest Q value in most cases. After executing the event, Q-testing enters the next cycle. Here we can see that because of the memory and state comparison, Q-testing tends to test the unfamiliar states. Additionally, the curiosity-driven exploration is a dynamically adaptive strategy. By adaptive, we mean that it can spot changes in the importance of states during the testing and will continuously adjust the reward for a certain event. In the following, we will give more details. The problem of reinforcement learning can be formalized with the Markov decision process. We can see from the figure that an Android application testing process can be viewed as a Markov decision process. The testing tool is like the agent exploring the environment created by the application behaviors. By giving rewards when testing action lead to new states of applications, the entire testing should be able to learn to cover more behaviors. We use the widget composition to represent states. This can be obtained using UI Automator, and the figure shows an example. Q-testing ignores some of the widget's attributes, mainly the texts, to avoid state explosion. The actions are the executable events inferred by analyzing the widget hierarchy. The widgets are arranged in a tree structure where non-leaf nodes represent layout widgets and leaf nodes represent executable widgets. By traversing this tree and analyzing the widget attributes such as whether clickable or scrollable, we can obtain the executable events. The transition function depicts which state the application will transit to after the event is executed. It is determined when the application is developed, and we cannot make any change to it. I want to point out that there are non-deterministic transitions in applications, which could cause problems to model-based approaches but not to Q-testing. The reward function gives a reward after executing an event. The design of the reward function is the key to our approach. It determines the efficacy of our exploration strategy. During the testing process, we adopt a curiosity-driven state exploration strategy. It has three main characteristics. First, through a memory set, it guides the test to explore some unfamiliar states. Second, we use a neural network to compare the states, which will be introduced later. In addition, we use the Q-learning algorithm to update the value of the action. We can see from the Bellman function that the value of the current action can be affected by the subsequent action. It is expected to achieve an optimal value after a series of updates. Here is a simple example. Before the test started, there was no content in the memory set. Q-testing first perceives the initial state of the application on the test and adds this state to the memory set. At the same time, it infers the executable events of the initial state. These events have the same initial values, which can be adjusted. Then Q-testing selects events with high Q values for execution. Here, we suppose that state 2 is similar to state 1 in the memory set, so it is given a small reward, and the Q values of the events are updated. Next, Q-testing uses a similar process to explore state 3 and state 4. Note that state 4 is quite different from the state in the memory set, so it will be added to the memory set and given a large reward. After a round of exploration, the Q value of each event have been updated. At this time, the Q values of the two events from state 1 are still the same. I want to point out that if we explore the same path again, the value of each event will be changed because of the impact of subsequent high-value events. The interaction event from state 1 to state 3 will have a higher value than the event to state 2. Therefore, in subsequent tests, Q-learning will tend to explore the path from state 1 to state 3 and then to state 4, making the unfamiliar states more accessible. We can now see that the state comparison is the key to the reward-given process. But how to distinguish states? We know two examples which are very different in GUI widget layouts and appearances, but actually they are of the same function implemented by the same piece of code. So we propose state division by functional scenarios. A functional scenario is similar to the definition of use case, which describes how users will perform the tasks. Typical scenarios include browsing scenario, searching scenario, and many others. In essence, we have proposed a coarse-grained state division method compared with the existing methods. Taking this case as example, the two states can transit to each other by scrolling the interfaces up and down. Their control layouts and other aspects are very different. Existing work will divide them into different states, but they correspond to the same functional scenario, which is watching some news briefs. If this kind of states cannot be divided adequately, The up and down scrolling events in this example will be well rewarded and will be continuously executed during the testing process. Our coarse-grained criterion can improve the efficiency of testing and help to allocate the time more efficiently. A natural question is why this module is implemented by neural network. The reason is that the existing feature extraction methods are difficult to meet our requirements. Using neural network can consider more dimensional features and at the same time get a better deviation threshold through just training. This is the model of the neural network. We used the Siamese LSTM. Specifically, the model contains two identical long-term and short-term memory neural networks, through which feature extraction is performed on the two layout files. Then, through the distance measurement, the similarity of the two states is calculated on the extracted vectors. The right side shows the process of preprocessing the layout file. We adopt different encoding methods for different data types. Q-testing only needs to use a part of the overall model, mainly the feature extraction part in the red box. The states stored in the memory set are actually the feature vectors. By saving in the memory set the feature vector, instead of the entire widget layout file of each state, we can save the time for repeated feature extraction and also save the storage space. Besides the curiosity-driven strategy, Q-testing also takes advantage of other strategies specifically designed based on characteristics of Android applications. Recycler view displays a collection of views in a scrollable manner. The clicking of all the items costs lots of time. Q-testing analyzes the results of the relevant events. If several items in a recycler view lead to similar states, Q-testing will ignore the items except the first one. Q-testing also takes system events into consideration. The random injection of these events can help in triggering intricate bugs. In the experiments, we first evaluate the effectiveness of the functional scenario division module. We collected a total of 6,058 pairs of samples. As the layout files are very structured, such an amount of data is enough in the experiments. We conducted 5 rounds of tenfold cross-validation. The division of the training set and the test set is conducted by apps, in case the data of the same app exists in both the training set and the test set, which will affect the experimental results. This is the box plot of the results. It can be seen that our neural network has a high classification accuracy rate, and it is feasible to use this model to divide the states and give rewards. The main goal of the experiments is to evaluate the test effects of Q-testing. We compared Q-testing with Monkey, Stoat, and Sapiens for 2 metrics: the code coverage and the number of errors found. We selected 50 apps from the relevant research work and Android app open source lists as experimental objects, and set the test time to 1 hour. This is the progressive average instruction coverage for each of the 4 tools over 1 hour test time. Our tool reached the highest coverage among the 4 tools in about 5 minutes, and it remained so until the end of the test. Overall, the average instruction coverage of Q-testing is notably higher than the other tools, which reflects the effectiveness of our curiosity-driven state exploration strategy. We also analyzed the test behavior of the test tools. Take good weather as an example here. Good weather contains a lot of configurable contents. We can enter the setting interface through the sidebar and then configure them. The difference in the coverage of the various tools in the good weather application is mainly reflected in the exploration of different configurations. We found that during testing, Q-testing tends to open the sidebar on the main interface. Monkey and Sapiens also have this tendency because they will inject some keyboard events during the test, and these events usually trigger events in the upper left corner of the interface. After opening the sidebar, Q-testing has about 30% probability to select the setting option, although there are many executable events to choose from in the current state. This behavior of Q-testing reflects its tendency of our state exploration strategy to explore unfamiliar states. The probability that monkey chooses the setting option is only about 13%, while the probability of triggering the first option on the top left corner is about 43%, the reason we have just discussed. We also counted the number of unique faults found by each tool. Q-testing found a total of 197 faults, the most of the 4 tools. We reported some of the faults to the developers. Up to now, 22 faults have been confirmed as the first-time discovered ones, and 7 of them have already been fixed. Now I'm going to conclude this talk. For automatic testing of Android applications, we propose a curiosity-driven state exploration strategy based on reinforcement learning. A state division method based on functional scenarios is also proposed. We implemented a tool and carried out a series of experiments which showed promising results. I'd like to emphasize that every part of Q-testing is essential to its success. The curiosity-driven strategy in reinforcement learning, the neural network-based scenario division method, the storage method of states, and the consideration of Android-specific features. Thank you for listening. Questions and comments are welcome.